Log on, tune in, find out. Another good idea from Cambridge.
By Malvina Luczak. Title is Vertices of High Degree in the Preferential Attachment Tree.
Okay, thank you for the introduction, and thanks to the organizers, one of whom is here, and for the invitation. So let me first tell you about the basic preferential attachment model. Okay. Okay, so this model goes as follows. So think of starting at some time, say, tau 0, positive integer value, and you're starting with some small tree on tau 0 vertices. Suppose something like this for tau 0 equal to 4, okay? So the tree has tau 0 vertices and hence tau 0 minus 1 edges, okay? And now there's a process, and this process is going to make jumps at times which are positive integers. So there'll be a jumps after time tau 0, and whenever there's a jump, what happens is that a new vertex arrives into the system, okay? And we're going to connect it by exactly one edge to one of the existing vertices. And now, how are we going to choose the neighbor for this vertex? Well, we're going to look at the degrees of the existing vertices. Okay, so here this vertex has degree equal to 3. Okay, this one has degree 1, 1, 1. And so when I'm going to choose the neighbor for this new arriving vertex, I'm going to choose it with probability proportional to the current degree of these vertices. Okay, so we attach new vertex by exactly one edge to one of the existing vertices of probability proportional to current degree. Okay. So there's one also very okay. So if you continue with this process, you're just going to at every time you're going to have a tree. Okay. So at time t, you will have a tree with tau, so t vertices and t minus 1 edges. Okay. But the fact it's a tree, actually, for the purpose of my analysis, isn't going to be very important because I'm not really going to be using any of the graph structure. Okay, and there is one sort of very simple variant of this process where, again, you start with some little graph at time tau 0 on tau 0 vertices, and then at every subsequent time you have one new vertex arrive. And rather than connecting it to the existing ones by just one edge, you connect it by some fixed number m edges, okay? And again, for every one of these m edges, you're going to choose its other endpoint with probability proportional to the current degree of the vertices. Of course, in this case, the graph will not really be necessarily a tree, but that's not important again, okay? So, so this process is really, the history of this process goes really a long way. So the first time, or probably the first time it appeared, was by Yule in 1925. So the process he considered was just slightly a more general version of this, so including the process I described here as a special case. And so this process is a so-called Yule process. Okay, and later on it was studied by Szymanski in 1983, and this was in the guise of so-called random recursive trees. Okay. Now, so that's sort of early days, but when this process became really important is 1999. So what happened in 1999 is that it was used by Barabasi and Albert as a model of the internet. So it's a very, very basic model of the internet. So you can think of the internet as a graph, and this graph sort of evolves over time. And I mean, in general, over time, you might have both nodes arriving and departing, and likewise with links. And here we just have arrivals and departures, but even so the basic idea is that it's an evolving model of the graph. And in the internet, I mean, you would think it's so intuitively that when some new nodes arrive, so when they make their connections, they will tend to go for those that already have quite a few connections, and that's why this is supposed to capture some of the key features of the internet. Okay, so this is this was sort of they studied this model rather informally, sort of most of kind of physics intuitive point of view. Now, a formal study of this model came from the perspective of its use as a web graph, came in 2001. That was by Bolobash, Riordan, Spencer, and Trushnadi. I'm probably omitting Hungarian accents. I'm very sorry about this. So one of the things they studied was the degree sequence of this model. So by degree sequence, I mean they studied the number of vertices of degree k for different values of k. Okay. Number of vertices degree k for different k's. Okay, and so what did they prove? Well, they proved that the degree sequence of this model follows a power law with exponent 3. And what this means is, in this context, that if I look at, let me call this dt of L, which is number of vertices of degree L at point t, okay? This number of vertices of degree L at time t. So they found that the expectation of this quantity, let me call it little dt of L, okay? So that behaves like a constant times t over L to the power 3, okay? So in fact, so the precise quantity is something like 4 times t over L times L plus 1 times L plus 2 plus something like 1 over square root of t up to the order of that. And they also proved that the actual random variable, capital dt of L, is concentrated around its expectation for L roughly something like for constant L, as well as sort of L varying with t, and going up to L equal to t over t to the power 115. Okay, so so concentration of capital dt of L around little dt of L for L less than equal to t to 1 over 15. Okay, I can tell you the precise form of this. The precise form of it is that if I look at capital dt of L divided by t, that's going to be less than equal to 1 plus epsilon times 4 over L times L plus 1, L plus 2, and greater than equal to 1 minus epsilon times 4 over L and L plus 1, L plus 2. So that's for any fixed epsilon greater than 0. And this will hold for all L less than or equal to something roughly like T2 1 over 15. And that's with high probability. And here with high probability means with probability as a probability tending to 1 as t goes to infinity. So as the graph gets bigger and bigger. Okay. So this is with probability approaching 1 as t tends to infinity. Okay. And in fact, the version we considered here was the version where you attach every new vertex by n edges. Okay. So now, what happened later? So later on, Szymanski considered this problem again in 2005, and he improved the concentration of measure results to go to roughly L less than or equal to T2 1 over 6. Okay. And he also considered another quantity, so the quantity that's number of vertices of degree at least L at time t. Okay. So it's number of vertices degree greater than or equal to L at time t, and that's of course just equal to the sum of the dt k's over k greater than or equal to L. Okay. So what did he prove for ut of L? Well, actually he didn't prove so much. The only thing that he proved for ut of L is just that its expectation is close to some constant times t over L squared, but he didn't actually manage to do any concentration. Okay, so if you take little ut of L to be the expectation of capital ut of L, then he showed that this is roughly twice t over L times L plus 1 plus some O of 1, but no concentration. Okay. So other work for this model, I think in the same year, Jansson, 2005, proved the central limit theorem for the dt of L's so joint central limit theorem, but in a topology that doesn't really look at what happens for L's tending to L is the function of t and tend to infinity with t. Okay. Now, what else? So one important thing as well that's due to Mori. I think that's also 2005. So Mori considered the maximum vertex degree for this model. So what he did prove is that, so let me call this thing capital delta of t. So basically capital delta of t behaves like square root of t. And moreover, if I multiply capital delta t by t to minus 1/2, that's going to converge almost surely to some random variable. Let me call it z. And this random variable, the limiting random variable in the law of large numbers, is non-constant. Okay. And also he proved that if I look at fluctuations of this thing from z, scale them up by t to minus 1/4, then that's converging to the central limit theorem. Okay. So fluctuations scaled by t to minus 1/4 converge, central limit theorem. Okay, so what is it that we have been trying to do? So this work that's joined with Guy and Brightwell. Our aim was to improve on these earlier concentration of measure results for dt of L and prove a concentration of measure result for ut of L, which we haven't got a concentration result until now. And how did we want to improve them? Well, in two ways. So first of all, the best results went something to like L to T to 1 over 6. And what you want to do is to be able to go further. You want to be able to go to T to 1/2, which is the maximum vertex degree. And secondly, is the order of concentration. So here, the order of the deviations. So here it's a bit weak, just to have 1 plus epsilon and 1 minus epsilon. So what you would expect is to have much better results, okay, than that. So here, so this is joint with Brian Brightwell. So the aim is to prove concentration of measure for dt of L and ut of L for L up to T to 1/2, roughly speaking. And the order of the deviation you should be able to control here should be like the square root of the expectation of dt of L, and likewise here, square root of expectation of ut of L. The way the process evolves with making sort of constant jumps over time, this is going to be the right order of the deviations. Okay, now there's a bit of a catch here. So if you look at dt of L, the number of vertices of degree exactly L, what happens at around, say, T to 1 over 3? Well, so the expectation of this quantity behaves like T over L times L plus 1, L plus 2 times 4. Now, if I take L, say, greater than equal to some constant T to 1 over 3, then this expectation is becoming like O of 1 as T gets larger and larger. So you can't really hope to have very good concentration of measure above this point. So what we do prove is just that deviations are with high probability no more than something like log of T for L greater than equal to some constant T to 1 over 3. I'll state a precise result shortly. Now, but for L smaller, more precisely for L less than equal to some constant T over log T to 1/3, we have what's roughly the optimal concentration of measure. So we can control deviations of dt of L from its expectation of order about square root of T over L to the power 3. Okay. Now what about ut of L, the number of vertices degree at least L at time t? Well, that's going to have mean that goes to infinity with T almost all the way to the maximum vertex degree up to logarithmic factors. And so for ut of L, we have concentration, so the control deviations of size around square root of T over L squared for L less than equal to square root of T, and we have some ridiculous log factor. It's log under the square root log to the power 13 of T. Now this log to the power 13 of T is not, it's just a technical issue. It's not really that you expect a good concentration to only hold until this point, but as the paper was getting longer and longer, we made the decision to, for the proof of concentration of the ut of L's, to reuse some properties of some recurrence relations we are studying for the dt of L's, and that led to a great simplification, probably cutting 20 pages of calculation, but we just settled for a slightly suboptimal result. Okay. So let me now give you a formal theorem to give you a flavor of what these results are like. So it's going to be somewhat technical looking thing. Okay, so before I do this, just make one observation. It's that if I look at dt, which is a vector with components dt of L for L greater than equal to 1, and if I look at the evolution of this over time, that's a Markov process. I will probably come back to this later and end up writing down transition probabilities of these quantities. But for the moment, what's important to know is the Markov chain. It's Markov in discrete time, but it's non-time homogeneous, so the transition matrix will change over time. And likewise, if I look at the vector ut with components ut of L for L greater than equal to 1, sure, you could think of it as a function of the thing here, but actually it's also a Markov chain in its own right. And so, yeah. Okay, so now let me state theorem. Okay. So I'm going to start, again, technical condition, we assume that the starting time till 0 is greater than equal to 4. And let me take some constant psi, which is greater than equal to 10 to the power 5 times square root of till 0 minus 1 times log of 3 till 0. So these are all constants. Okay. And now let me start with graph G0, any graph with till 0 vertices and till 0 minus 1 edges. Okay. So any graph with till 0 vertices and till 0 minus 1 edges, and we consider the preferential attachment process starting with this graph G0 at time till 0. Okay, so we consider process starting with G0 at time for 0. So then with probability greater than equal to 1 minus 4 over psi, we have the following. We have that dt of L minus 4 times t over L times L plus 1, L plus 2, absolute value of the difference between dt of L and what is roughly its expectation is at most 120 times square root of t times log of psi of t over L to the power 3 plus 301 times psi squared times log of psi times t. Okay, and with probability at least 1 minus 4 over psi, this bound holds simultaneously for all L greater than equal to 1 and all times t greater than equal to 0. Okay, so it's for all L greater than equal to 1 and t greater than equal to 0. Okay, so let me comment on this result. Okay, so psi is a constant which determines the probability of something bad happening. Something bad happening meaning that one of these bounds fails for some L and some time t. So obviously I can choose psi to my liking, as big as I like, to have my desired desirably small probability of something bad happening. But if I choose psi quite big, obviously these results will only be quite interesting for t large enough. Okay, so if I choose some psi big, so need t bigger than some t0 psi for this to be interesting. And in particular, I mean, when is it interesting? It's interesting when the first term dominates the second term, because the first term is the deviation of size roughly square root of the mean up to a logarithmic factor. Okay, so we want first term to dominate the second term in size, so that makes you choose a big T for this to be interesting, even though the bound as such holds for all T's you like, but it only tells you something really interesting for T large enough. And secondly, also the L comes into play. Okay, if I want the first term to be bigger, much bigger than the second term, so it dominates, well, I want to have square root of T log T, you forget the psi for this purpose, being much bigger than log of T. And so what is this reducing to? Well, if I can forget about the log T here and have a square root of log T instead here, and then I can forget the square roots, and it basically tells me that I need L smaller than T over log T to 1/3 for this to be for this to give me the right order of the deviations asymptotically as T goes to infinity. Okay, so that's what this is doing. Okay, so this is the result for the dt of L's, and we have an analogous result for the ut of L's, looking just about equally technical as the first one. So what do we have for ut of L's? So it's the second theorem. So let tau 0 be greater than or equal to 4. And now we choose psi greater than or equal to the maximum of two things. One is tau 0 and the other one is 10 to the power 5 times square root of tau 0 minus 1 times log to the power 3 of tau 0. So again, these are constants. And again, we start with some initial graph G0 at time tau 0 with tau 0 vertices and tau 0 minus 1 edges. Okay. And here, with probability at least 1 minus 4 over psi, we have ut of L's ut of L minus 2t over L times L plus 1 less than or equal to 45 times square root of t times log of psi t divided by L, and plus 4 times 10 to the power 9 times psi times log to the 7 of psi of t, and that holds for all L greater than or equal to 1 and t greater than or equal to tau 0. Okay, so it's a similar looking thing. There's a first term which is supposed to be the square root of t over L squared up to a logarithmic factor, and there's a second term which is similar to what we had earlier but has a higher power of log, and this corresponds to this log of 13 to the power t, which is the bound on where we how far we can go in L to have a meaningful concentration result for ut of L. And yes, so this is one more comment. When L is equal to 1, actually this is not very interesting because number of vertices of degree greater than or equal to 1 is just number of all vertices, which is always t. Okay, so it only has meaning for higher L's. Okay, so now what's interesting about the second theorem is that it seems to be in fact the first explicit concentration of measure result for UT of L. Okay, so this is first explicit concentration of measure result for UT of L. Of course, one can deduce some fairly weak results from what was proven earlier about DT of L's. So in particular, the result I stated earlier by Bolobash, Jordan, Spencer and Tushnadi. So when their result on the concentration of measure shows that for small l, for constant L, DT of L has concentration of measure with deviation of around square root of t, which for constant L is roughly optimal, and one can deduce from the result the same for UT of L, but only for constant values of L. Now something else, so UT of L is the kind of variable that, I mean, if you've worked at all with applying Talleyrand's inequality, so UT of L is the kind of variable you might hope to apply the Talleyrand's inequality to, not DT of L itself, but UT of L. And one thing you want to do, if you want to apply Talleyrand, you want to find the so-called certificate. So if UT of L is greater than or equal to x, I need to find a certificate of a small length. So very roughly speaking, sort of enough small length in terms of coordinate to show that indeed certify that UT of L is at least x. Because the idea of Talleyrand's inequality is thinking of the random variables of interest as being a function of some finite number of independent random variables. And then the certificate is, okay, if I know that UT of L is at least x, I need to produce a certain number of these independent coordinates with particular values to certify if they take these values, then my function has value at least x. And it turns out that for UT of L, you can find a certificate. So if UT of L is at least x, you can find a certificate of length at least of length roughly x times L. And if you plug this into the Talleyrand inequality in the usual form, you're going to get concentration of measure for UT of L up to L around t to 1 over 3. So that's not optimal. So the existing methods that have been used for this problem have not produced optimal answers. And Talleyrand's inequality, as far as I know, has not been applied in the literature, but one of the tools we considered before coming up with the solution we used in the end was trying to see what happens if you apply Talleyrand. And it only gives this, only goes to t to 1/3, which is not optimal. And if you wanted to then use it to produce concentration of measure for dt of L, using the fact that dt of L is equal to ut of L minus ut of L plus 1, you're only going to go to like L equal to t to 1/4 for the dt of L. So again, you're way, way away from the optimal, even though that was going to be still an improvement on what was already known in the literature. Okay, so the methods we have used, which I'm going to talk about shortly, but we're hoping they will work more generally for other preferential attachment type models, and actually more generally than that for other Markov processes, because we have come up with some inequalities that potentially can be applied rather generally. Let me just tell you before I talk about the methods, one other preferential attachment type model, which is supposed to be sort of the most general preferential attachment model encompassing the sort of the original ones. That's called a Cooper-Friese model, and that's from 2003. So how does this work? Well, again, you start at some time for 0, and you have some sort of graph. Doesn't need to be a tree, whatever you like. And now the evolution is going to be a bit more complicated. So at every step, I have a choice, actually. I'm not always going to have an arrival of a new vertex, I only have an arrival of a new vertex with probability alpha, and with probability 1 minus alpha, there will be no new vertex arriving. Now, if a new vertex arrives, then I'm going to connect it to the existing ones by a random number of edges. So at time t, it's going to be mt, and these mt's will be all IID and with bounded support. And so in the event that I have introduced a new vertex and I are connected by this random number of edges to existing ones, I choose then the second endpoint of each one of these edges independently, and it's chosen with probability beta by preferential attachment, meaning with probability proportional to the current degree of the vertices, and with probability 1 minus beta uniformly. Okay. So for every one of these random number of empty edges, I look at, I do this random choice independently, and it's a probability beta as we have in the model I introduced at the beginning. So with probability proportional to the current degree of the existing vertices, and with probability 1 minus beta, I just choose uniformly. Okay. So that's in the event when with probability alpha a new vertex arrives. Now, when no vertex arrives, I still introduce new edges. So I'm going to have nt edges at time t that happens with probability 1 minus alpha. And again, all these nt's are IID and bounded support. And for each one of these edges independently, I'm going to choose the first endpoint. So you can designate one of your endpoints as the first endpoint with probability beta 1 by preferential attachment and 1 minus beta 1 uniformly, and for the designated second endpoint the same but with probabilities beta 2 and 1 minus beta 2. Okay, so it's quite a bit more complicated, and it turns out to really encompass many other versions of the preferential attachment model. Now, despite this very complicated look, there seems to be a key parameter which seems to determine its behavior. So this key parameter is called eta, and it's given by alpha times beta times the expectation of m1. So these mt's are IID, so just I'm taking expectation of the first one, plus 1 minus alpha times expectation of n1 times beta 1 plus beta 2 divided by twice alpha times the expectation of m1 plus 1 minus alpha times the expectation of n1. So what is this parameter eta supposed to be? Well, it's basically the limiting proportion of endpoints of edges that are attached by preferential attachment. Okay, so it's limiting proportion of endpoints chosen by preferential attachment. So for the model I've just discussed, for the special preferential attachment tree, what happens is that alpha is equal to 1, okay, so then you can just forget about this lot and this lot, okay. Then also beta is equal to 1, and so you end up with, well, m1 is also equal to 1 with probability 1, so you just end up with eta being equal to 1/2, okay. Now, why is eta important? Eta is important because, again, this model has a power law for the degree sequence, and eta is the key parameter that occurs in this power law. So here, if I look at dt of L, again, number of vertices of degree L at time t, that's going to behave like some constant times t times L to minus 1 over eta. Okay, so Cooper in 2006, extending earlier results by Cooper and Fries from 2003, he showed that expectation of dt of L behaves like this with value of constant which he determined, and this holds for L less than equal to t to 1 over 6 and also less than equal to t to eta over 3, okay? So it has to have a bound which is, so L has to be less than equal to both of these things. And he's proven some fairly weak concentration of measure results as well for this range of L's. So his result looks like as follows. The probability that dt of L minus the expectation of dt of L in absolute value is greater than equal to the expectation of dt of L, I think, divided by square root of log t. That probability decays like 1 over log t. So it's not really very strong result, since we're not doing much better than just looking at deviations by the size of the expectation. Okay, so you would expect, again, much more than this holds. And what would you expect? Well, you expect the concentration of measure to persist for L's up to roughly t to the power eta, which is the maximum vertex degree in this case, roughly speaking. And again, you would expect to have concentration of the optimal order, so roughly of the order square root of expectation of this, which is like square root of t over L to 1 plus 1 over eta. Okay, and likewise, you would expect similar results to hold for the number of vertices of degree at least L. So for this model, our work is still in progress. So there are some technical issues in our computations which result from the fact that the number of edges you add at every step are random. It's obviously not a serious problem because they're all IID, but technically it just introduces some complications into our methods. So let me now spend the last 15 minutes or so talking about our proof methods. Okay. Okay. So the proof is just roughly relies on analysis of Markov chains using martingale techniques, but tailored to the particular issues we have to face for these models. I won't say tailored to the particular model, but say tailored to particular requirements that these kind of models throw at us. So we analyze. So the basic process one has to look at is some Markov chain X with components, say xt of k, okay, and the point is that the k's, say, there aren't just finitely many k's. There are countably many of them potentially. So it's a Markov chain with countably infinite dimension, and part of the important issue is that these different components will jump at different speeds. Okay. I mean, for our case, if you think of xt of k being equal to dt of L, well, what kind of speed does it jump at? Well, for it to jump, for most values of L, you basically have to choose a vertex of degree L or L minus 1 as an endpoint for a newly arriving edge. And that happens with probability roughly dt of L over total number of endpoints, just twice t minus 1 at time t. And so if I substitute what this thing behaves like roughly, it's going to, I get the t cancelling out, and so I get something like roughly proportional, some constant over L to the power 3. And so clearly the speed of jumps are very different for different values of L. And the question is how to use it. Okay, so let me just write down some basic martingale and super martingale that I used here. So if I have such a Markov chain, and let me take some function f, which is defined on the state space, we call it E, and takes real values. Okay, so the Markov chain, suppose it's a non-homogeneous Markov chain in time. So it say has transition matrix pt at time t. So let me now write down the following thing: empty superscript f to show it's that it belongs to the function f, and this is equal to the value of f at time as a function of xt, so the value of f when you evaluated the value of the Markov process at time t, minus the initial value, okay, and then minus basically the sum or the integral of the jumps, okay. So I have a sum over s from 0 up to t minus 1, and sum over all possible jumps y. So ps, which is the transition matrix at time s, so the probability that I jump from xs to y, and the resulting change in the function f. So I multiply this thing by f of y minus f of xs. Okay, so roughly empty f is the value of the function f at time t minus initial value minus integral of its drift. So that's going to be a martingale under very mild conditions on the function f. Okay. And the key issue is to be able to analyze the deviations of this martingale. And we do this by introducing a suitable super martingale. So if I take any function g, again on space E, taking real values, let me introduce zgt, okay, equal to the following. First of all, I have g of x of t divided by the initial value g of x0, and now times the so I'm going to go on another board because this is I've got too little space here. So zg t is g of x of t divided by g of x0 times the exponential, and the exponential is the following thing. So again, I have a minus sign at the front, but I have a sum over s from 0 to t minus 1 and sum over y. And now I'm going to have, again, p s of x, s, and y, so the probability I jump from xs to y. And then I have g of y minus g of x s, and divided by g of xs. So it turns out that, again, under fairly mild conditions, just in showing that all the expectations are finite, this is going to be a super martingale. Okay. So these objects are mainly used in the context of continuous time processes, which meant we couldn't really apply any ready results, and we had to do everything from scratch because nobody seems to have bothered doing anything in discrete time. So now the key is to analyze the deviations of martingale MFT. I'm going to use zg for a suitable choice of function g, and in fact my function g will be g of x equal to e to the power theta times f of x and minus f of x0 just for, it's not really very important, it's x0, but just to simplify some presentation, x0 is the initial state of the Markov chain. And so if I plug in this g for my chosen function f that I want to analyze, then this z is going to take a nice form, which will allow me to then use the optional stopping theorem to estimate deviations of the function f. So in fact, with this choice of g, my zgt will be equal to the exponential of theta times m superscript f at t minus the sum over s from 0 to t minus 1, something I called phi, phi s, a kind of superscript f of xs, xs and theta, the function of xs and theta, and it's roughly going to be the variance of the jumps. So precisely, this theta, so this phi function, the phi function is given as follows. So phi sub s superscript f of x and theta is equal to the sum over y of ps of x and y, so the probability of making a transition from x to y, times e to theta times f of y minus f of x minus 1 and minus theta times f of y minus f of x. So basically the exponential of the thing here in the bracket is basically the exponential of theta times f of y minus f of x, but minus the first two terms in Taylor expansion, which makes then this quantity being roughly 1/2 theta squared times the sum over y ps of x and y times f of y minus f of x squared. So roughly, indeed, it's the variance of the jumps of f, okay? And so working with this, we have managed to write down some nice inequalities for deviations of martingale m, but this is not the end of the story. In fact, it's not the interesting part of the story. So, so let me tell you what is really different and interesting about the method. So, the issues of particular application we have for the method. So, to get concentration of measure for number of vertices of degree L at time t, I need to consider the process D with components dt of L. So I need to write down the suitable martingales for each one of these dt of L's. Okay, so let's look at the drift. So if I look at, say, the drift in dt of 1, okay, so it's the expectation of dt of 1 minus dt minus 1 of 1 given the state at time t minus 1. So what happens? Well, I'm always going to get new vertex arrive. I will always have degree 1 afterwards. So this is equal to +1. And I'm going to lose a vertex of degree 1 if I choose a vertex of degree 1 as a neighbor for my new vertex. So I have this happens with probability proportional to dt minus 1 of 1. So I have a term dt minus 1 of 1 divided by twice t minus 1. And I do the same thing for dt of L's for other L's, and I end up with expectation of dt of L minus dt minus 1 of L given dt minus 1 is equal to L minus 1 times dt minus 1 of L minus 1 divided by twice t minus 1, and subtracting a similar term with L, but not L minus 1. So minus L times dt minus 1 of L over twice t minus 1. Again, it's just about the probabilities of choosing a vertex of degree L minus 1 or vertex of degree L as a neighbor for a new vertex. So having done this, now I obtain martingale equations that I'm going to work with. The equations are as follows. So we have dt of 1 is equal to d tau 0 of 1, that's where I'm starting, plus the sum over s from tau 0 to t minus 1 times 1 minus ds of 1 over 2s, and plus the martingale, which I call mt of 1, the martingale corresponding to this component. And this is dt of 1, sorry. And likewise for other value of L, that's for L greater than or equal to 2, we have dt of L equals to d tau 0 of L plus the sum over s from tau 0 to t minus 1, L minus 1 times ds of L minus 1 over 2s minus L times ds of L over 2s, and then plus a martingale term which I call mt of L. Okay. Now, so I want to compare these recurrence relations with random quantities to deterministic recurrence relations obtained by dropping the martingale term. Okay, so I want to compare the random variables to function xt, where xt of 1 is equal to x tau 0 of 1 plus the sum over s from tau 0 to t minus 1, 1 minus xs of 1 over 2s, and xt of L equal to x tau 0 of L plus the sum over s from tau 0 to t minus 1, L minus 1 times xs of L minus 1 over 2s, and minus L times xs of L over 2s. So what I want to show, and that's the whole point of this game, is to show that dt of 1 is close to this deterministic thing, which is basically the expectation, and likewise with this being close to this. And I have to do this by controlling these martingale bounds. So now what you do is you write down the recurrence relations for the errors, for the differences between these things. So first of all, this xt of L is the familiar thing we saw earlier, which is 4 times t over L plus 1, L plus 2 plus some error, the term which depends on initial condition, roughly speaking. And so now, if I write et of L equal to capital dt of L minus little xt of L, I obtain recurrence relations for et of L from these. And skipping the details, I end up with et of 1 being equal to et minus 1 of 1 times 1 minus 2 over t minus 1 plus delta, mt of 1, that's the martingale difference, mt of 1 minus mt minus 1 of 1, and then likewise et of L for L greater than or equal to 2 is equal to et minus 1 of L times 1 minus L over 2 t minus 1 plus e t minus 1 of L minus 1 times L minus 1 over twice t minus 1, and plus again a martingale difference term. Okay, and we try to deal with these inductively and with little luck in terms of trying to get optimal answer. So instead we wrote it down in a matrix form. So first of all, note that you can in fact truncate the process at some L0 because any given component L only depends on the earlier indices. So if I truncate this, I get a set of L0 equations. And I can write this in matrix form as ET, which is the vector of errors, ET with components ET of L for L less than equal to L0, equal to AT minus 1 times ET minus 1 plus delta MT. This is a vector of martingale differences. And these are matrices. And matrix AU is given as follows. So it's got non-zero things on diagonal, and it's got 1 minus 2 over U, then 1 minus 2 over twice U, and so on up to 1 minus L0 over 2U if you truncate at L0. Then it's got something just below diagonal, so it's 1 over 2U, and then so on up to L0 minus 1 over 2U, and the 0 everywhere else. It's a substochastic matrix. And I can then get an explicit formula for the error, ET, as follows. ET is equal to the sum over S from tau 0 plus 1 up to T of the product of the matrices AT minus 1, AT minus 2 up to AS times martingale difference delta MS. Now what's the issue now? I want to analyze this error using martingale inequalities. But the problem is it's not a martingale. Okay? Even though I have martingale differences multiplied by something, it's not a martingale because this end of this product changes in time. But I can have a way around it, and the way around it is to fix some tau, fix some quantity tau which is bigger than tau 0, and consider something called m superscript tau tilde, which is the same thing, except I change the end of the product to be not a t minus 1, but a tau minus 1. Okay? So I have a sum over s from tau 0 plus 1 up to t, and I have a tau minus 1, and then up to as delta ms. And that's for t less than equal to tau, and I stop it at time tau. Okay? And the thing with this is that this is equal to my error at time tau, okay? So E tau is equal to m superscript tau tilde at time tau. So now this is a martingale, and I can obtain the bounds on the error E by studying this martingale for every possible time tau. And the issue is, how do I see it as a martingale corresponding to a Markov process of the type we looked earlier? Because it doesn't seem to be obviously any function of my Markov process dt. So it turns out that you can introduce a new Markov process which consists of dt and also something called dt tilde. Now, dt is what we saw earlier, and the dt tilde part is basically something, it jumps whenever dt does, and when it jumps, it makes the same jump as dt, but it's multiplied by this matrix product at time s. So I'm scaling, so they both make a jump at the same time, with the same rate, and there's the same vector involved, the same jumping vector, but for dt tilde, I multiply the jump by this matrix product, okay? And then this is a Markov chain, and this martingale turns out to be of the right form for this Markov chain to enable me to apply the martingales for martingale techniques I described earlier. And then what it ends up being reduced to, being computed, to computing a particular bound. So let me write down this bound, and then I'll stop. So anyway, if you look at this like that, I end up having to compute the sum over s from tau 0 to tau minus 1, sum over y of ps of ds and y, and then I have the jump of ds, so y minus ds, multiplied by this matrix product, a tau minus 1 up to as. And then I take the Lth component of that, okay, and I want the variance of jumps. So I take the square of these. So this is this quantity corresponding to the sum of the probability of transitions times the square of the jump. And this is a square of the jump for the function in question. And when you compute this, you'll find that it's very difficult. That's pages and pages of computation. You find that this is of the right order, which is tau over L to the power 3, roughly speaking. And then the martingale deviations of the error is of the size of square root of that. And hence you get the optimal concentration of measure bounds, optimal up to logarithmic things. So because it's so difficult to compute this for the basic preferential attachment tree, that makes it even harder to do it for this more general Cooper-Freeze model. There's even more computation involved, but we're hoping to do this as well soon. I mean, we already have made a lot of progress, but at the moment we're just still fighting with the computations of this thing. So thank you very much for your attention. I'll stop here.
Are there any questions? Just a naive one. Is it also studied when you would attach differently according to, I don't know, powers of the degree or the something?
I think there is some work. I can't tell you the names of the people off the top of my head, but I think people looked at various versions of this, which are sort of superlinear, sublinear, so depending whether you take a power greater than 1 or less than 1. And I think one of these cases isn't very interesting for some reason, but I forget now exactly the results, but there has definitely been some work.
Did it change anything?
It doesn't change anything in the principle of it, meaning that there is going to be a Markov chain and you can do this kind of thing, but probably it can change a lot of the actual calculations. So I can't tell you what happens. Just because computing these matrices. So basically, the vectors y here correspond to these different transitions. So basically, you lose, say, you acquire 1 in a component in the first component, then you lose a 1 in some k component, and acquire 1 in some k plus first component. So you've got these two vectors which are not completely trivial for the change. Multiplied by these matrices are not diagonal, but have 2 rows, and then take the Lth component and square and then sum it. So this is supposed to be summing on a good set. So basically you have a good set where your ds doesn't deviate too much from what it should be, and then you want to show that it can't do that because while it's good, these things are small and so actually it can't really get out of a good set. But it's so bad for this simplest model that it might be, I don't know, it may be worse when you introduce powers, but in principle the method is very generic and will work for any Markov chain, but with varying degrees of complexity depending on what happens.
But if you have nonlinear like preferential attachment function, then
Yes.
you do not have the matrix equations anymore.
Well, I don't think so, because the matrix equations are just to do with Markov chain. It's not to do with a particular form of transitions. So I doubt that something is going to change, actually. There will be some equation. I know because...
So you have the nonlinear here.
Well, there will be some equation, but I mean, these components will change, obviously. But having this matrix form for the error, I think it only really relies on having a Markov process. It doesn't rely on anything else. And just being able to act as a vector, everything. So Markov processes are linear, even if their transitions look non-linear in L, but the Markov chain still is a thing, it's a linear operator. So I still expect to have the linear structure. It just will look very different.
I'm sorry to keep on this point, but as I said, I mean, one of the major things that made this tractable is the fact that you have in the denominator over there an easy function of time, just twice over t minus 1.
Again, I don't think that's really important either.
Saying that if instead you have some, because otherwise, if you're considering, for example,
Yeah.
the degrees the square of the degrees, then you need to sum over the square of the degrees, and you have to
Yeah, I still don't think it's, I mean, the linearity only comes in having these components. So it's going to change the look of this, but, you know, and it may make it intractable computationally, I can't say otherwise. But the actual structure of the proof is really very general. It just works for any Markov chain, as far as I can tell. I mean, I know partly because I originally tried to apply this kind of technique in a very different context with a very different chain. So as I know it's possible, but yeah. I mean, one thing which makes it easier for me to work with discrete time here is the fact that I can do these matrix products. If you went in continuous time, I think that's going to be messed up, and I don't know, have some integrals, I guess, but maybe worse than computing a discrete product.
So, no more questions. Thank you very much again.